view and going live. And looks like we are live. Just gonna wait till it actually shows up on my YouTube here so I can mute myself there. Okay, that's good. We are all set up. Hi, everyone. Welcome again. Some of you have joined us before and some names I see new here, so that's pretty cool. Thank you for joining us. This is our next topic, our next talk in this guest speaker series that we do here at SJAA. And it's been, I was just explaining our speaker today how we moved the whole thing to be virtual, and it's become very popular now virtually as well. So that's been pretty cool. We also are starting our events to be in person a little bit now. We are doing star parties again, and we are doing some solar observing as well, daytime observing. And our library is also open sometimes during those events now. And all of these events and updates are shared mostly through our meetup, but also if you're an SJA member, you should also get an email about it, and you can go with that. So either way, I hope you're getting up-to-date information about our events. If not, feel free to get in touch with me through Meetup, or you can email any of the board members, and they will be happy to answer your questions as well. Now, with that introduction, I would like to take a couple of minutes to introduce our speaker tonight. Uma Gorti, she's a scientist at SETI Institute. And as we were just chatting, it happens that we are from same city in India, which is Mumbai, or Bombay, as Uma likes to call it. She did her master's degree from IIT Bombay and did a PhD from Indian Institute of Astrophysics in Bangalore, India. And then she moved to US for a fellowship and working from NASA Ames, UC Berkeley, and then now at the SETI Institute. And she has been doing her research in planet formations, which is the topic she's going to talk to us about today. And I'm very excited because I know I heard her speak at another event not too long ago, right after James Webb was launched. So with that introduction, Uma, the floor is yours.
Thank you very much, Sugata, and it's my pleasure to be here. I hope I make this interesting enough and worth your time on a Saturday evening. My talk today will be on planet formation, and that's really a trick because I'm really going to be talking mostly about protoplanetary disks. And right on this title slide, you can see that I have our solar system with all its planets. And one thing that is sort of strikes out at you right away is that they're all aligned in a plane in a disk, right? So it's very clear that, and it was clear to people hundreds of years ago, that our solar system must have formed in a disk. So, and I can't advance the slide. Sorry.
That's okay.
Why can't I advance the slide?
Yeah,
now
it okay. There we go.
So, and we now actually we know that there are planets around other stars. We found hundreds of these planets, and if people are not aware of this site, I sort of encourage you to go look at it. It's exoplanet.eu, and they're sort of updated with all the confirmed planets with all kinds of manners of detection. So you can detect them because the eclipse in front of the star. You can detect them just by radial velocity, which is basically the fact that they sort of exert this dynamical tug on the star, and you can see them and of course you can directly detect them in some cases if they're big and bright enough. So all these planets are compiled together on this website, and I've just sort of pulled something out here. And you can plot various things against each other. So it's kind of interesting to just explore if you have the time. What I've plotted here is the frequency versus mass from this website, and you can see that there's kind of two peaks, and there's a preferred mass. There's two preferred masses here. And that this is the frequency, which means the number of planets you have for a given mass, right? And there's clearly a distribution of some kind. It's not flat, so there seems to be two preferred sizes. And of course, you don't see things that are too small or too big. And so we know now the planets are quite common around both low mass stars, stars lower mass than the sun, and also stars that are maybe a few times the mass of the sun. So this is what we call intermediate mass stars. And planets are common everywhere. And so how about these? So it turns out that in general, as far as we know, they all form in a disk, right? So the geometry is like that of very thin disks. And what I have here is our solar system again at the bottom. So this is the inner solar system. So this is another system called TRAPPIST-1, which also has many planets just like our solar system, but they're all really packed very close in. So you can sort of see that, they're all inside the orbit of Mercury. But nevertheless, they're in a disk. And the same thing is true of, for example, Jupiter and his moons as well, right? Which you must have all seen. So the fact that they're all in a disk suggests that the similar sort of physics that goes on when these planetary systems form, and then that they all form in these disks. And so again, I'm having trouble with, yeah. So we can sort of compile these planets, and there are some trends that stick out. So one of them is that these super Earths and mini Neptunes are very common. Super Earths are basically planets like the Earth, but larger, considerably larger, a few times larger. Mini Neptunes are sort of, planets like Neptune, but smaller in size. And these are things that we don't have in our solar system, but they turn out to be the most common planet if you look at extrasolar systems, exoplanetary systems. Cold giants are also quite common. And what else do we know? Well, we know that so this is all from the planetary statistics, that after you correct for all sorts of biases, you find that there may be about, at least a couple of planets per sun-like star, and that multiplanetary systems are more common, just like how we have multiple planets. And not only that, it looks like almost half of all stars have planets. So planets seem to be fairly common. So what else do we know? That they're all close in. So this is a sort of a peculiar result, which was kind of, surprising when we started detecting these systems, that many of these things have, several Earth masses worth of material all packed inside one AU, and they're not as spread out as our solar system, for example. And of course, giant planets are common, mostly around 1 to 10 AU. And if you go out or in, you sort of find them dwindling in numbers. And not only that, there seems to be some dependence on planet mass, with the stellar mass in that low mass stars have lower mass planets. So having detected all these planets, we see that there's enormous diversity in these exoplanetary systems, right? So they're all very, very different, and very different from our solar system, which is completely unexpected. And it's now thought that they mostly reflect the sort of disk that they form in, right? And we'll get to that in a second. So they reflect the disk conditions under which they form. And so the first thing is I'm going to place all of this in context, is that protoplanetary disks are really protostellar disks. And the word proto just means, that, they're sort of the birthplaces of these planets or stars. So before you even form the planet, you're actually forming the star. So I have here a cartoon. I'm going to show you actual images later, but it's kind of easier to imagine or understand what you see if you sort of look at this cartoon, right? So this is kind of how star formation progresses. You have a dark cloud. So this is that dark cloud. I really mean very dark. It's about 10 degrees Kelvin, hardly radiates, and you'll see that soon. And then there's some kind of condensation in this cloud, which is made of hydrogen mostly. It collapses for whatever reason, some sort of galactic dynamic processes, or some sort of dynamical processes, and something happens. This thing undergoes gravitational collapse. And because these cores are also spinning, they form a disk, and then material accretes on the disk, and then that sort of proceeds through to the center and then forms your star at the center. And this is kind of how stars form. So the disk sort of facilitates this whole process of star formation. So you first form the disk, and then material sort of flows through the disk, spirals inward, and then collects right at the center, and that's how you have a star. And the same disk also forms planets. So after you finish forming the star, so you sort of over here, and then somewhere along the line, you also form planets. And then eventually you see systems like these. So what you're seeing here is a disk, and it has carved out some channels. The planets have carved out channels around the disk. And eventually, after some time, the entire disk disappears, and you end up with a planetary system like what you see here. And planets form somewhere along so these two stages is what we think currently. This is sort of what we call the planet forming stage of the disk. And now these are actual images, right? So so you could now go back and think about what you just saw. This is the dark cloud, right? So you can see that it's dark because you're looking at the stellar background, and in front, you're sort of obscuring all the background stars. And you can see that this is really a core. So there's a blob of material out there, and the only way you know is because it's blocking out all the background stars. This isn't the visible, but if you go in the infrared, which is a different, just sort of towards the red end of the spectrum, so the sort of like the heat, that's in the infrared. you see that there is actually a star at the center, and you can see it. It's not visible in the visible image, but you can see that there is a bright. So this is the same field, and you can see that there is a bright spot in the center. So this is your forming protostar. What you're looking at here, and this is the next stage, which is a disk. And again, you don't really see the disk, right? The disk is sort of edge on. So it's this dark lane that you see in the center over here. That's the disk. You're not seeing it. What you're seeing in this visible image is light. So the central star is sort of scattering light at the dust at the surface. So you can sort of imagine a bowl, and you're looking at sort of the surface of the disk, and that's what makes it look like that. And so you're looking at, and of course, it's symmetric. So you see a bowl on top and a bowl at the bottom, and that's sort of being irradiated by the star, which is also obscured in this case, and it's in the center. And then there's a jet. We're not going to get into the jet, but there's also material, there's magnetic fields and things which sort of cause these jet motions. So this is the disk. And then later on, the next stage, you sort of, or maybe concurrently, this is at the same time, perhaps, you see a disk, and this is actually the disk. And you can see here that this disk is initially quite massive, and because the disk is massive and it's gravitating, dynamics usually means that you form spiral arms, just like you see, for example, in galaxies and so on. So this is a massive disk, and you can see that this is the image of the disk. You can then image disks at a slightly later phase. And if you remember, I showed you this image of cartoon of a disk which had planets in it, which were sort of carving these channels. And that's what people think you're seeing here. So you're seeing a disk now. This is face on. It's actually pretty thin in the Z direction. So you're looking at this disk is inclined. So you're sort of looking at it face on, and you can see that there's sort of no material in these lanes, which could be a planet. And of course, there's also no material at the center, which is another thing. And so this means that this suggests that there are planets in there. So this is a system that has already formed the planets. You can actually see forming protoplanets. So there's, this, I'm not going to get, so I'm not going to get into this, but, so these things are believed to be protoplanets in this disk. This is the disk around the system. And there's these two bright spots here are believed to be protoplanets. So these are planets that are forming. And then much later on, you end up with a planetary system. So this is a planetary system. So this is a star. It's got 4 planets that were detected. And in this particular case, you could actually see the planets. So these are planets that are visible and detectable directly. And you can follow them. And then you can see that they're actually moving in these orbits. And these arrows sort of indicate how the planets are moving around. So you see the planets, and you also see them moving around. So this is sort of what we know about planet and star formation. So how can we understand planet formation, and how do we explain that enormous diversity that I told you exists in the beginning, which is that you have all these, different kinds of compositions, you have planets distributed all over the place, and you have a certain sort of multiplicity, why you form multiple planets in some cases and you don't in others. And how do we understand this? And that really boils down to understanding how do we understand the disk, because this is where they form. And a very simple thing to assume, which is probably correct, is that the reservoir of material available dictates what forms, right? So you're forming them, that's the raw material you have to begin with. And not only that, if they have different compositions, for example, or if you're forming planets in different locations, this is also perhaps just a reflection on the sort of disk that we have. Maybe large disks form large planetary systems like ours. And this, I'm just sort of speaking unscientifically here. This is just speculation. I'm just trying to get you to think about it. If you have smaller systems, then maybe disks, maybe you form things much close by, or so basically that's kind of what we think, that the protoplanetary disk conditions reflect the sort of planet formation and diversity that you see. And so what do we know? So now we're moving on to disks now, and then what do we understand from disks, and how do we understand planet formation, and what can we actually see? So again, here, this is a similar sort of image like I showed you before. In the visible, you see this cloud, but then if you look in the infrared, you can see the disk, which is this lane, and then you can see the jet around it, right? So we know that, okay, the disk is not visible, is not apparent in the visible, but you do see it in the infrared, which means that the disk is cold. The disk is not very hot because it's not hot enough to emit in the infrared. And the disk, we know already, it forms from the interstellar medium, which is basically the galactic molecular clouds, and that consists mostly of hydrogen. So that's sort of the dominant component. And it also contains solids, right? So it contains small suspended dust particles. And this is a real dust particle, is an interplanetary dust particle. This is the kind of thing that is embedded. So it's kind of a dusty cloud, right? So that's kind of what it's made of. And these dust particles are silicates, kind of like the sand we have on Earth. And they're very small. They're submicron in size, which is like you probably know what a micron is. So you have, and this is the interstellar medium material that you're actually forming the disk out of. So we know that, okay, this is the reservoir that the disk starts with, right? And then what you see here is I have these four boxes here. So this is showing you flux, which is basically the brightness as a function of wavelength. So this is the wavelength along this axis. And then I want you to sort of pay attention to these things. So this is a sequence of images. So these are four curves. And the first one is the class 0. So it's a cold black body. And you can see if you pay attention to this light gray sort of region, it's sort of moving towards the left and it's getting brighter. So this is really the star, right? So this is the central star. It starts out cold, and then as you accumulate more and more material, it starts eventually getting very hot and then starts putting out light. And this is really now we're sort of talking about the visible wavelength out here, which is sort of a micron or so, right? Which is what you see. And then now pay attention to this little darker blob of gray. So there is nothing to begin with, which is just the cloud core. And then at some point, you sort of have this huge excess in the infrared. So you have this, large sort of emission here. And then it continues to stay fairly large, and eventually it drifts away. So this is the disk. Sort of it shows up here right after the core forms, and then it sort of eventually disappears and the star takes over. And this is kind of what we first saw in our cartoon, where we started off with a star and then ended up with a disk towards the end, right? And so this is for, I guess, I realize there are people who maybe this is too technical, but the idea is that, so how do we know what's happening? So the shift in wavelength, how does it tell us that it's getting hot? It's because things of different temperatures. So this is the brightness, again, is a function of wavelength. And it's what's called a black body, which is like the sun, for example, is a very good black body. And that just means that the material and the radiation are sort of, are all talking to each other and they're really in equilibrium. So that means that, and then it has a very characteristic sort of emission spectrum. So they all look like this. So the sun sort of is pretty much like a black body. It's at 6,000 and it peaks in the visible. And if you go to cooler objects, if you go to 5,000, you can see that this peak sort of shifts to larger wavelengths. So that's kind of how you tell that the star is getting hotter and that the disk sort of stays cold. And that's one way of doing it, right? And so what else do we know? Well, you can collect photometry, which is basically what you're doing is now you're looking at how much light, you're looking at a bunch of disks. And so this is one kind of study you can do. So this is a slightly complex plot, as I'll walk you through it. What we have on the x-axis is age. So, how old is a system? And you do this by looking at clusters, because it's hard to just look at a star and say, well, it's this many years old. It's usually hard to do. It's much easier for looking at clusters, and this is how stars form. They all form in these groups, and you must have seen them in the sky, the Pleiades being one such example, right? And then what you can do is you can actually, if you have a cluster and you know that they all are bound together, but then they have this very characteristic sort of evolutionary track, and that as they evolve and they become older, they follow this evolutionary track. And based on that, clusters, it's a sort of a statistical way of estimating the age. It's much more reliable. So what's plotted here are a bunch of clusters. So this is like this is a young cluster, NGC 1333. This is Taurus, and this Chameleon, there's Orion, which you're probably all familiar with. So the two clusters in Orion. And then there is Upper Skull, which is there's a cluster in Upper Skull. So you're sort of looking at all these individual star-forming regions. And then because you're looking at clusters, you can sort of place their X point, right? You know where they are. And now what you're doing is, this is infrared measurements done with Spitzer. So this is the IRAC bands. You're looking at a few microns. And then you're looking at this. So if you see something, you take a cluster, so let's say it's got 100 stars, and then you count out how many of them are showing disk emission, right? And so then it turns out that that's 80% for the young stars. And as you go to something like Lambda Ori, which is 4 million years old, only 20 of those stars will have disks around them. So it's sort of seeing how many stars have disks. And you can see that this is following a very nice sort of an exponential decay curve, right? So this is telling you something very important. And what it's telling you is that the disks have a lifetime of 5 million years. And so this looks like a lot, but really in the context of how long stars live. So the sun, for example, is 4.5 billion years old, right? So in that context, this is very rapid. It's like the first few weeks in a human life, for example. So what that means is that planets need to form within 5 million years, because remember, the disk is where the planets form. So the disk is going away. That means planets are finished forming. We already saw that from the previous slide, right? Because you just sort of have these channels carved in there. And so planets are forming very early. So what that means is that now you have a problem in that, well, the disk is going to disappear. So your planet formation process needs to be very rapid. So this is one thing you've learned just by looking at disks and just by looking at their continuum emission. And we sort of, so in maybe about now nearly 10 years ago, not so much, but so we have this new facility called the ALMA sub-millimeter array. So this is a radio telescope. This is in the Chilean Andes Mountains, and this is a plateau up there, and the sky is fabulous there. So basically you have this is a partnership between ESO and NSF and Japan. And so they have this facility which has a bunch of antennas. So these are radio antennas, kind of dishes that you might have seen. And so they have a sub-millimeter array. And with all of these, you can get much better resolution. You can see fainter things. And this is one of the first images that was released with ALMA, which is HL tau. And before ALMA released this image, you didn't have any image. It was basically, this was an object inside a cloud, right? And you didn't even know there was a disk. And people did not even realize that disks were present that early. So this is a 500,000-year-old object, and you can already see channels in it, right? I mean, this is the thing. So this is just 500,000 years old, and so it could be that these are not planets. I mean, that's quite possible because there are quite a lot of them. It's still unsettled. But the first thing you can think of is, yeah, I mean, planets seem to form pretty young. We're pretty early on. So you have this very embedded, enshrouded disk, and this is why you need facilities like ALMA, because if everything is happening when it's all covered with material and you can't peer in, then you don't have any hope of understanding or observing or finding out how do planets form, because you can't, basically that's inaccessible to you. So you have to resort to these sorts of things, which is like basically the millimeter array. And the reason that you see this is because the dust is optically thin, in that it allows light to pass through, so you can peer in deeper. So it's kind of analogous to what you saw before, right? Remember when I showed you the core and the protostar a few slides ago, you couldn't see anything in the visible image, but then when you go to the infrared, which is a longer wavelength, you start seeing things, right? And the same thing the JWST images do. You must have seen plenty of them now, that if you compare them with Hubble, you can peer more into obscuring material. And this is going to a complete extreme. So you're going not just from the visible to the infrared, you're going all the way to the sub-millimeter, right? So you're going really long wavelengths. And you can see that this has given us a lot of information. So this is most of our understanding of disks has changed with ALMA data. And a lot of what the data I'm going to be showing you after this is all from this particular telescope and facility. And again, this is to show you that these are edge-on disks. These are 3 disks, and these are, again, they're all seen in this one you're looking at face-on, but if you look at it edge-on, so this is what we saw before. So we saw those bowls again, the one that I was talking about before. So you're seeing, so this is a Hubble image. And with Hubble, you don't really see the disk. The disk is this fat little thing, this dark thing in the center, and you're not seeing it. You're just seeing the upper surface, the scattered light image. So most of planet formation is actually happening where the matter is, which is in the midplane, and it's only with ALMA you can probe this. And these white bands you can see here are ALMA continuum images, and you can see that in the millimeter. So this is another such disk. You can see that it's slightly tilted, and you can again see emission here. And this is a third disk, and you can many of these. Obviously, there's a lot more data, but I'm showing you how you can peer into these regions which are in the middle of the disk, right? And which is presumably where planets form. And you can go to even longer wavelengths. So this is the VLA. So now you're going into radio wavelengths. You're going to centimeters. From millimeters, you're going into centimeters. And this is the Orion cloud. And this is another such study where all of these little dots are basically sources, these yellow dots in the cloud. So stars form in molecular clouds. And each one of these, you can see that there's an ALMA image and a corresponding VLA image. And you can see that they're quite different, right? I mean, so you get different information based on what wavelength you look at. You can ignore this. This is just a this just is a cartoon that shows how a disk forms. Again, it's the same kind of thing. You have a core, then the core forms a disk, you have this outflow, and that's kind of what you're seeing in these images here. So this is again, but now a lot of what I showed you was dust, which I already told you was a small little suspended particles in this. Most of it is gas. 99% of it is hydrogen gas, right? And with other things. But you can't really see this. And so somehow, if you're trying to now form planets and you say, well, where's all the material going? What's happening? Even for the dynamics, for the conditions, like how hot it is. I mean, so the gas is sitting over there. It's a huge mass sink, and you do have to know what it's doing. But unfortunately, these lines, it doesn't emit like that black body that I was telling you about that the dust does, right? I mean, the gas emission is very different. So what you're relying on here is these are atoms and molecules. They have different levels. And the electron systems, I don't know how many of you have done, some of you must have at least done some chemistry. So this is, this is a whole bunch of quantum mechanics here. And there's like probability of electrons decaying, they emit photons, and this is a whole complicated process. And the lines are very, very faint. So this is a spectrum from a star, and you can see that, the little blips. So this is the emission. So this is what you see. You don't really see a continuous sort of emission like you saw in the case of the black body that I showed you first, where you just had something hot and it showed you sort of just saw this emission at all wavelengths. These are very specific. So for example, OH will emit, so OH is basically when you break water, you get this OH radical, and it emits only at these particular frequencies. Neon, for example, is emitting right here, right? And then these are some hydrogen lines, and if you have carbon dioxide, it's emitting right there. So there are, so they don't really emit everywhere. They emit in certain regions, and it's a little hard to put together this information and try to understand what's happening with the main component, the gas. But you can nevertheless do a few things. Like, so this is, for example, CO, which is a very the next most abundant molecule after hydrogen. Hydrogen turns out is very light, and for various reasons you can't really see it. So because it's not very bright. And so the next best thing is CO, which is usually how most gas studies are done with CO. And this is it is like about 10,000 times less abundant. That means that for every hydrogen molecule, for every 10,000 hydrogen molecules, not 10,000, there's 4 hydrogen molecules, there will be one CO molecule in abundance relatively. But even then, it's very bright because it has a dipole. It's C and O are not of equal mass, and so that means it can rotate, and therefore it emits very easily, unlike H2. So you can see that, so this is a survey. So all these disks have been observed with ALMA, and they all look very different. And you can see that, some of them are bright, some of them over here are very faint. So one of the, and so we think that, okay, so CO is a proxy for H2, and one of the most pressing questions today is, what is the mass of the disk and how does that evolve? So we don't even know how much material there is in the disk. So for example, we saw remember the plot that I showed you before, which said the disk lifetime was 5 million years. It was just showing you a statistical thing, but it wasn't really telling you, well, you're not going to be able to take one disk and then see how much mass it has and how that is evolving, because the timescales are too long. And so that's kind of what happens, if, so with this, that you don't really, you don't get to watch a disk form planets. You also don't get, it turns out it's also very difficult to just take this disk and say, well, how much mass does this have? Because that will tell you something. Like, you can sort of make a mass statistics out of the disk, but it turns out even that's quite difficult to do. So you can't really take this emission and convert it to a mass very easily. And not only that, it turns out that there's enormous diversity. This is another ALMA large program. So this is 5 disks. And so we're looking here now at the same species. So we're looking at HCN. This is a bright emission molecule that you see towards many disks. And there are 5 disks here. And you can see they all look very different. So one of them is huge, the other one is, is tiny, then there's one of them that has a ring. And so they all are, and then this other one has a ring too, which has got a hole in it, but this one is sort of centrally concentrated, and they all look quite different in terms of if it's just one molecule. And not only that, if I take the same disk, so for example, I just pick this disk, and then now I look at different molecules. I can look at CO, HCN again. I can look at these other molecules. And you can see each one of them actually looks different, right? It's the same disk. But if you look at it in H2CO, it looks very big. It looks very big in 13CO as well. But if I look at HC3N, it's really tiny. So not only that, these molecules are emitting in different places. And this chemistry is important because it could tell you something about the kind of planets you form, right? I mean, so, and what is the composition of the planets? I mean, what will it have? Maybe if you form planets everywhere, so maybe if you form something really close in, you form these, these kinds of organic species, and if you form them way out, maybe you have something else. It's telling you, so this kind of tells you what material is available where, and this is of interest for people like us who are trying to understand, how do you go from the disk material to planets? And so this is sort of the last slide I have on the data, which is again telling you, which is showing you that, not only that, you can actually nowadays see embedded protoplanets. So this is Subaru, which is a optical telescope on superimposed ALMA data. And then there's this little blob here, which is an embedded protoplanet. You can actually see it in some cases. And then there's another one over here. It's the same disk. And so you actually see it move, and that's how you tell it's a planet, because you can actually see it moving around the sun, moving around the central star in some orbit. And over here, this is another image where this is a recent work again, where they actually see a circumplanetary disk. If you remember, I showed you, I think in the very second or third slides, that Jupiter has a system around it, right? It's got its satellite system, and this satellite system is also in a disk. And you can actually, that formed from not a circumstellar disk, it's from a circumplanetary disk. And this is sort of a disk around a forming planet, and this is also being detected. So this is sort of just information that we have. So now, okay, so we've got some information. Clearly, we don't have in everything we need to know, but we've got various bits of information. You can piece that together, and you can start to think, well, how do planets form, right? So there are two main planet formation scenarios. I'm just going to go over them very quickly. So there's an accretion model. In this model on the left-hand side, you start with those very small submicron dust particles I showed you, and then you sort of very, very slowly over multiple, many years, you kind of stick together. So two particles collide and they stick, and they slowly grow from that submicron size, sand-sized particles to huge things, right? So you have to form a rocky core first. And this rocky core, once it gets to be about 10 Earth masses or something like that, it can start accreting gas and you can make giant planets. So this is one way of doing it. And this is always thought, and this is a challenge because you have to sort of, you start from these very, very tiny things and you have to build up to something as big as a planet. An alternate scenario is, you start off and the disk is really, really massive, and then you have, there's a instability, which means the disk sort of goes gravitationally unstable, and then it forms clumps, and those clumps then sort of just collect together and they form the self-gravitating planet, right? And that's another way of doing it. But it turns out that, and this is like, you have to form this early because you can form this early because you're doing this in a stage where the disk is very massive, and so things can happen fairly early. It turns out that the overwhelming evidence is sort of pointing towards core accretion, largely because, if you formed it at this stage, you have to have a lot more gas giants like Jupiter everywhere, and it turns out you don't have as many, right? You mostly form these rocky things. And so which means that you can't have formed it like this. You still need the gas to be present because, that sort of, it dictates the dynamics, and otherwise things would just be scattered all over the place. But you do know that these things are all sitting in disks. So there was gas, but it's not accreting it like this, right? So, so there are a few objects, I must say that there are, in fact, quite a few objects that do form in this scenario. So it's likely that both of them take place, but overwhelmingly, it is thought that it's core accretion or this kind of a slow bottom-up scenario that makes planets. And this is a complicated plot, but it's kind of just to sort of give you an idea of what the sort of things that happen, because it's a very complicated environment. So this is a disk and there's a slice through it. On the left-hand side, you can see that there's dust. It has to do the whole planet growing business. So the little dust first settles down, and then it sort of collects together. It forms these little cores, forms bigger things, and then they also move. They don't just stay where they are because there's dynamics. Things are spinning around. They experience sort of a drag, and then they sort of slowly spiral in. And then there's all kinds of things. They could even, some of them could even accrete onto the star and just go all the way in, because remember, the star is also forming. So this material in the disk is not just staying put. It's actually all funneling in towards the star. And this is sort of what happens. And then not only that, when all this material is piling in, the star puts out UV and X-rays. The young stars are very bright in ultraviolet and X-rays, like maybe 1,000 times or 10,000 times as bright as the sun is. So they're really very bright. And then all that radiation then impacts the disk. And on this side, you have the gas. It drives wind. It heats the surface and drives winds and gets rid of the gas. And then it does a whole bunch of chemistry, which this is sort of responsible for those plots I showed you before, where I was showing you every different molecule. So those are all sensitive to the UV photon flux or the X-ray flux, because then molecules break, and there's a whole lot of chemistry that happens. So this is a very complicated system, and and we're sort of looking at pieces of it, and we have to sort of put all of this together. And so it's going to focus mostly just on the dust. And just to tell you what happens, so these are the main things that happen. One of them is that they can get mixed, so that the dust is churned around. So that's called turbulent mixing. It can cause radial motion. It can cause vertical motion. This is a slice through the disk, by the way. So this is sort of a disk, and I guess it's obvious, but it's, just thought I'd point that out. And you also, these grains, or the bigger ones of the grains, when they become big, then they settle down, just like how things sediment. They settle down to the midplane of the disk. Because of gravity. And then you can also have things that kind of move in at different speeds depending on how big they are. And then grains can also collide. So two of them collide and all of them don't stick. Only some of them stick, but some of them shatter and they break. And there's a whole bunch of things that go on with these grains. And you can look at them, it turns out, in different wavelengths. And that's sort of where JWST would, for example, see the upper disk, and then you can see the midplane with ALMA. And depending on what wavelength you're looking at, you can get different clues as to where this emission is coming from. And you can, to some extent, probe some of these processes, even though it looks very difficult to do. But the main challenge is that it turns out that it's very difficult to grow particles to meter sizes and beyond. So with all the physics that we know, we can go from a micron to maybe about a meter. But then that's not where you want to stop. You have to go all the way to maybe about 10 Earth masses, or if you want to form something like the Jupiter, and you even have to form, for example, the terrestrial planets, right? So meter size is about the most, you don't seem to get past that. But if for whatever magic, you form these 10 to 100 kilometer size objects, then it turns out now you have gravity to help you, because once they become large enough, they start pulling in things, right? Because you've become massive enough and gravity sort of pulls all the objects together, and then suddenly you can grow to planets. And if gas is present, then you have this large Earth mass sized core that can accrete gas to form giants. So the two main hurdles. One is you growing past the small sizes, getting past this meter barrier, as they call it. And the other is that in the time that it takes to grow these Earth mass sized cores, you might have gotten rid of the gas because the gas is gone. So you want the gas to be there, and you want this to happen like in 5 million years, right? So many present studies on planet formation focus on trying to speed up this growth by various mechanisms. I'm not going to get into them. I think I'll skip the slide. I think it's a little bit too technical for the audience, but if you want, I can leave it here for a second. But this is basically just, so this is a way in which you can clump these things together. So it turns out that there is this process called the streaming instability, which is what people think. I mean, this is one of the most popular theories right now, although there are other theories as well. So in this sort of a case, what happens is that you have these small particles, they're going around, but then, the particles are but the gas has got, they feel the gas, it's a headwind. And so they lose angular momentum, which is basically the sort of spiral in slowly. And then what happens is that you have enough solids, then they can sort of affect the motion of the gas, and you start sort of clumping things up. And that's kind of what you're seeing here. You take a little slice of the disk and you do the simulation. This is a simulation, and you can see that things are clumping up, and then eventually you form these little objects. And sort of this is, and you can have particles clump fast, and this is sort of a promising theory because you can get past that meter size barrier and form larger things. I mean, there's still lots of details to be ironed out, but that's something. So once you have a core, then you can start sweeping up material. You can grow to rocky-sized planets, and if you have a really big planet, a core in the center, you can also start accreting gas, like I said before. So planetesimal formation, which is the formation of the first 10 kilometer size things, is the bottleneck. So once you achieve this, planets can accrete and grow rapidly. And we don't really know how this happens. So this is, and of course, we also want all of this to happen in the presence of gas. So this is kind of what the same thing I'm sort of showing you, that you go from the micron size all the way to Jupiter size, which are 10 to the 6 meters and so on. So this is a log scale, which means that so this is the micron, this is millimeter and meter, and so this is each of these little things is a decade in size. So you're sort of starting from here, you're growing to pebbles, then you're sort of making this planetesimals in some very rapid way, which is what this arrow is supposed to indicate. And then you have this growth after that, and you can maybe accrete gas and form planets. So once, so except for the giant impacts, because there's going to be some rearranging of everything after the planetary system forms. So that then determines where things finally end up. But there's basically, this is sort of the thing. And so I thought I'll end the talk. The last few slides are mostly on my work, just to give you a flavor of the sort of things I do. So this was the whole overview of planet formation and disks. I study mostly on disks. So this is what I do. And I just thought I'd end with that. And what do? I study things like how long does a disk last, right? This is one of the things I'm interested in, and how do you get rid of the material, because this dictates how much material is available. So I've got a couple of slides of a few figures here. So one of them is showing you how it's a simulation of how the density changes, goes down with time at a given radius. This is density versus radius, and this is a simulation where there's thermal wind. So basically you're heating the surface, and that's kind of just evaporating away. So we're more recently doing a different sort of wind, which is a magnetically driven wind. So it's really a plasma, the magnetic fields in disks that thread through the disks, and these also cause their own dynamics, and you can actually have winds that are driven because of magnetic fields, and we're looking at that. So this is a simulation of that. I'm also interested in how quickly you can convert things into planetesimals. So here, for example, you can ignore this plot, but over here you can see that we have the mass that you're building as a function of time. So these are the small grains, and then so this sort of goes down with time. And eventually over here, this blue stuff is planetesimals, and you're forming them by that streaming instability mechanism I told you about before. So here in this case, we only end up converting about 100 Earth masses, but this turns out it doesn't really form in the right place. But this is sort of just the work that we're trying to sort of test some idea out here. I also look at emission. So this is like, for example, CO in one of these, we look at the composition, and by modeling, we're constructing these mathematical models. So this is ALMA data at different velocities. And so the contours are, I think, the ALMA data, and the background is the model. So we're trying to match build a model that can represent the data. And we found that in this one disk, all the CO that's being produced is because comets are colliding, is what we think. This is disk where, there are lots of young comets which are being formed, and they're all colliding and releasing all the CO, is what we think. So you can sort of do that. We also look at things like, for example, what is the mass of disk? So this is like we're looking at the emission of some CO line, and we again build models, and we try to see, well, how does the gas and dust mass change, and sort of trying to do, so we're basically trying to put together pieces of the puzzle in various ways. And other work I do is also, so we sort of have these models. This is a disk, it's a slice to the disk. This is the radius and the height. So it's basically, you can think of a torus, and I just sort of cut in vertically, and then you can see a slice. And then we look at what kinds of ices are present in the center of the disk and their composition. And then the sort of data then guides experiments at Ames. So there are people at Ames who sort of create ices in the lab, they get them irradiated with UV photons. And it turns out that this often forms organics. So this is one of the things that you see. And these organics are then obviously are sort of the raw ingredients for the origin of life, and sort of trying to see, well, where would you form life? Because it turns out there's a lot of what they call abiotic chemistry happening already. You already form things like amino acids, for example. So it's not like, you wait for Earth to build. You actually have a lot of chemistry that goes on at very early stages. And it's thought that, things like asteroids and comets probably bring these sort of primitive prebiotic materials onto Earth, which then allow life to take place. So this is sort of also some of the work that I've been doing. So this is my last slide. And so the main takeaways are that planet formation is a common outcome, and all stars have formed via disks, and looks like most of them form planets. The disks are very short-lived, which means that planets must form very quickly. And the conditions in the disk determine whether planets form and what types of planets form. And that the disks are very chemically diverse, which means that you expect naturally that the planets themselves are going to be diverse like you see them. This is something that JWST will probably tell us more about, what sort of planets and compositions they have, which is something we're sort of waiting very eagerly to see. But and it's quite likely that they do, because even in our solar system, for example, you do know that all the planets have different compositions, right? And they're not all made of the same thing. And so disks offer a unique window into planet formation processes. And also, you can also use this to see how organics and primitive life might perhaps originate in different parts of the disk, and how common this might be. So thank you for the time.
Let me unmute myself. Thank you so much, Uma. Well, it's time for questions. So you can put your questions in chat, or if you want to unmute yourself. I had to mute some of you during the talk. I was getting some background noise. Sorry about that. But if you want to unmute yourselves and ask your questions, that's fine too. So go ahead. Wow, quite crew today.
So is the large number of planets that are close into their star within 1 AU or thereabouts, is that observation bias? Because both Kepler and TESS tend to favor detecting planets that are close in and have short period orbits.
Yeah, so that is, you can correct for that sort of thing. That's very right, because you are looking for transits. But so even if you correct for the observational bias, it turns out that you do have, even with radial velocities, for example, you are sort of biased towards looking at things closer in. But even accounting for that, it turns out that having planets close in is quite common. It's quite, so we sort of, so right now our observational techniques are biased towards either looking at things really close in, or things really far out where you can actually, they're far enough, but then they have to be bright, and you sort of see them, for example, giant planets. But it's still a result that is thought to be valid in that, even if you account for the bias. Yeah.
Anything else? So I'm curious about James Webb. Like, of course, that is gonna surpass the current telescopes in like what it offers us. So are there any specific projects that you have in the works right now using the James Webb Telescope?
Yeah, so I think that James Webb will particularly be interesting for in the context of the talk, will be interesting for figuring out what planetary compositions are. I think that, and connecting those with disks. I mean, right now we have no clue what they contain, right? So we do know, we have some idea of what the disk chemical composition is. So that might tell us something. But that's not something I work on. But some of the James Webb projects I have been involved in mostly look at winds, which is kind of what I'm interested in. So they look at, how you're losing material. I work mostly on the gas component, really, not really the solids. I mean, so there's a lot of atomic and molecular physics and radiative transfer and that sort of thing. Like it's different kind of physics. But then, yes, I'm interested in trying to look at the winds. So that will be something that because they do two things. One is that they answer these winds are believed to carry angular momentum, because a very fundamental process in the disk, which is really not very well understood, is how does the material actually move in, because you do need that to happen, right? And it is happening all along, and you sort of see material accreting onto the star, but really how that's happening and the physical mechanism by which it happens is not known. So one of the ways that's been sort of proposed theoretically is that you have these winds sort of taking away angular momentum, these numeric winds, and thermal winds are also present, but we're sort of trying to do both these things, look for the presence of winds, and that's something that the James Webb will hopefully do. I hear we have some data, but it's not all there yet. Yeah.
Okay, cool. Thank you. Anyone else? Don't be shy.
There was a question by Gary. Was a direct message.
Okay.
What is
he sent it to you. That's why I didn't see it.
Okay.
Yeah.
What is your best guess as to how common an Earth-sized planet will have a life-friendly climate as opposed to having little or no atmosphere? So I think that Earth-sized planets are probably common. I mean, I think there'll definitely be many more. We already know some. And whether they will have water, I mean, water actually is, when I say life friendly, there are many things in there, right? So one of the first things I can think of is water. We need to have water, obviously, and probably liquid water. So there is, water is actually very common. It's one of the most common things in disks. I mean, there is water everywhere. The Earth have formed dry, but you have to have the Earth stay in this habitable zone or something like that. And I think we already have some planets which are sort of Earth-like, which can have an atmosphere and which are in the habitable zone. But beyond that, I think, we don't really know how life originated and what all the different things that have to come together for this to happen. But just based on what I see, I mean, for example, you already see complex chemistry out there, and it's quite likely to happen everywhere. It's quite possible that that it would have there would be life-friendly planets out there. And as to how common, I think you're asking for a statistical number. I don't think I can hazard that guess. I mean, in terms of, I would say that it would be fairly common, right? I mean, it's not, it's at least, let's say it would not be uncommon. I definitely think there are going to be some planets out there. Whether life actually emerges or whether, maybe it stops at just being bacteria, who knows, right? So that's also something we really know very little about that kind of thing.
Sorry, I joined a bit late. So initially when the star is forming, how does the separation between the gas that forms the star and the gas that forms the disk happen?
So there is no separation. So it's all happening simultaneously, right? So the only way to think about it is the planets have to form late, because as long as you're funneling in most of the material to form the star, even if you did form, let's say you were forming planets willy-nilly all over the place as well, those planets would also be funneled into the star, right? So they would just be eaten up. So it's quite possible that you're making planets, by whatever process, let's say you make planets and they're funneling in, but they're going to get accreted on. So it's only the ones that once the star is more or less assembled and material is not trickling in, because this accretion rate, or the rate at which the star is collecting mass, is initially very high. It's like 10 to the -5 or -4 solar masses per year, and then it keeps going down, right? So it takes it goes down very drastically. So maybe it's towards the end that those are the ones that will survive. So it's not really, there's not really a distinction, and because we don't know when planets form really, it's quite possible that they form right at the beginning. One doesn't really know. So there is not really much of a I would not say that they are two separate. It's more like two separate epochs or times, but not really different conditions otherwise.
Got it. Thank you.
Sure.
So early on in the accretion model, what sort of chemistry is probably going on? Is it just electrostatic sorts of things holding it? Obviously, it can't be gravity. They're not big enough particles for it. So is electrostatics, or is surface ices freezing things together? How does it work?
So the early process, I'm sorry, I didn't quite catch the first part of the question. You're referring to the growth of particles, or?
Yeah, the growth of particles.
Yes, right.
Model.
So it is just plain sticking, right? So they are all ice coated. So everything outside, let's say you have, typically disks are a few hundred astronomical units in size. And given how hot stars are, and most of the disk outside it may be a couple of AU or so, it has ices on them. So they're water ice on them. And water ice is sticky. So when two grains get together, they just collide and they just stick, right? So this is not, so this is just plain collisional sticking. And you could, so now again, whether you stick or whether you break when you grow, because there's a chance that you fragment. So that depends now on the velocity of the impact, right? I mean, so if you have two grains that are they hit each other at great speeds, then obviously that would shatter them rather than grow them. But most of the growth is rather gentle, and you can actually model that with just fairly simple physics, in that if you know what the temperature is, you can sort of calculate the distribution of velocities, and then you can calculate a probability. So some of them will collide and stick, and some of them will sort of just break. And typically in disks like that, with these processes, you can grow things to maybe about a centimeter size, and it's a function of density. So if you're closer in, maybe you go, a few lucky particles might get to like maybe a few centimeters or so. So beyond that is you have a challenge. So up to there, I think, and they do it, and they have to actually have lab experiments. They do experiments in the lab where they take sort of similar particles and then they shoot them with, against each other with certain velocities, and then they watch what happens. And so these are experiments people do to simulate this kind of thing. And they do know how this changes, or what kind of velocities will break particles and what will allow them to stick. And this is the sort of thing we input into our models. We sort of put these lab experimental results based on composition to figure out whether things stick or not. And when you put them into the models, it turns out that under this typical disk conditions, you can grow them to maybe a centimeter sizes or so. And beyond that, you need some magic, like the streaming instability, for example.
Cool. Any other questions?
Well, this might not be a very, smart question, but I'm just curious.
Yeah.
How, just in terms of Alpha Centauri is our closest, star neighbor 4 light years away, I believe. So what are the, closest stars which have shown anything approaching even, decent sized planet? Thanks.
Actually, I think Proxima Centauri, which is pretty close, does have an Earth-sized planet, and I think that there is a probe being planned to be sent to Proxima Centauri. It does have like it has planets, and it's pretty close. It's like, I think, 4.5 light years away, and it does have a Earth-like planet, a suburb, and it has a super Earth as well. I think it has 2 exoplanets. And I think that there's talk about, at NASA at least, about trying to send something there soon.
Wow.
Yeah, it's
Cool.
yeah, it's not going to be in our lifetime, I suppose. But, yeah, deeper distances are great, and obviously,
Well, I mean, perhaps the bigger question I was getting at is that, I mean, basically something faster than light travel would need to be available for any of this to make, anything other than, I mean, star, I mean, obviously it's good to know about star formation and, the physics involved, but other than that, it just doesn't seem to me to have any, any other sort of benefit, or at least it just seems that people are projecting their fantasies, about habitability and whatnot. But
I don't think so, because okay, so I will I beg to differ. So I think yeah, it is to some extent it is philosophical. So this is like, it's just like any other pure science, right? I mean, it's more for knowledge than for any, and I think anything that's a benefit is mostly just spin-offs, like NASA has spin-offs, for example, for its technologies and things like that. But there's no tangible benefit, right? But it's just sort of, just understanding our place in the universe kind of a thing. And so there are, you can sort of, there are this very active research going on in areas like looking, for example, for indications of biosignatures, even technosignatures, right? I mean, you can sort of, if you have, for example, an advanced civilization, how would you detect, how would you detect things that, whether you can detect, if there's a characteristic sort of, signature of, let's say, photosynthesis or something like that, right? So let's say you're looking at Earth from somewhere very far away, and you happen to have the right sort of instruments, and you could see that, okay, if there is plants in this photosynthesis, there's a certain kind of signature you'd expect, and that sort of a thing I think is very probable, and it's probably pretty close on the horizon as well. I mean, this is not something I'm talking about maybe a decade from now or something, but we might be able to do something like that. But it's not. And I think that is interesting enough, just the fact that there is life out there, right, of some kind or the other. I think that's possible to do. But whereas if you actually see civilization, if you think about how long the Earth has been around for and how long we've been around, or how long there's been, technologically advanced civilization, now you're talking about a much smaller fraction of time, right? And then, yeah, then that's sort of, that's less likely, but but it's still possible, just given the sheer number of the sheer number of planets out there and stars out there in the galaxy. You might just be able to detect something, but then whether you can actually like make contact with civilization, I mean, that's probably not something that it's not what drives most of our research, actually. I mean, this is more sort of just love for pure science and sort of trying to understand our place in the universe, right? I mean, how we are here, kind of a thing. It's and it's a fascinating question. That's my take on it anyway.
I learned about this in class the other day about the Eagle Nebula and how like expansive it is compared to our solar system. I just wanted to hear your take on it.
Oh yeah, no, it's actually the Eagle Nebula is it's a star forming region. It's what they call massive star forming regions, where they have like a really massive star, like just like Orion, right? So it's got it has I don't remember what the central star is, but it's got a cluster in it, right? And so these bright stars, they're O stars, they're very, very bright, and they put out a lot of light, and they're like maybe 30 times the mass of a star, but they're like 1,000,000 times brighter than our sun, for example. And they blow away the surrounding cloud material. That's what, as soon as the stars are formed. And when they blow that away, you get these pillars. So that's what you see. I think you're talking about the Eagle Nebula pillars, right? So you see these very, very dramatic,
yeah,
right? And what they do is that they actually have these they sort of blow the material around them, and then they also compress it, like so you have winds from all directions, you can take material and you can compress it, and they also trigger star formation. So maybe there were clouds where they would not have formed stars, but then you have pressure on it and you're sort of compressing it, and then that can form stars, and they've seen evidence for that as well. And this is something that JWST has probably already has a release on the Eagle Nebula, I think, if I'm not mistaken, or maybe I saw something that I think it is one of the targets, and you probably will be able to see disks forming in the Eagle Nebula. So then usually low mass stars form that way, so we have these big stars, and then they push material away, and then they compress the cloud surrounding them, and then they start a new wave of star formation in the cloud. That's typically what happens.
Thank you.
Sure.
Oh, lots of interesting questions. It is an interesting topic. I mean, I'm not surprised.
Yeah, it's complex and there's a lot going on. So that's kind of what keeps me interested in it. But there's no obvious answers to things, right? I mean, so you have to think about how it's going on. Yeah.
And then there's the curiosity of just like, oh, there are planets forming everywhere else. And then what happens when, like, somebody asked about the extraterrestrial life. I think that's where I think one aspect of it where everyone is very curious about it.
Yeah, no, I mean, yeah, it's a very interesting question. It would be great if there was, there were people out there, right? But yeah, it's, I think it's also in a sense humbling, right? If there isn't anybody out there, that's very humbling, right?
Exactly.
Yeah,
exactly.
it's because the universe is huge, and all of you who look out at it, telescopes will know, right?
Yep. Sure. All right. Well, let's see. It's one last round of questions, if anybody has any. Okay. Well, I guess that's a wrap then. Thank you so much for joining, everyone. And thank you so much, Uma, for this wonderful talk. And I'm gonna stop streaming now before I actually terminate the Zoom meeting.